Hello! Thanks for watching and giving me the possibility to share my enthusiasm about the Sentinel-2 mission with you. Because, in my opinion, that mission is outstanding. While orbiting the planet, the two satellites produce roughly 10 terabytes per day for both top of atmosphere and bottom of atmosphere data, namely L1C and L2A. And as a result, we get beautiful pictures. But of course, it's not only about the beauty of our planet. Actually, mainly it's about the analysis of it. For example, water, fire, ice, and vegetation issues. For the CHEMODIS project, we need efficient and consistent access to the data, especially L2A, so bottom of atmosphere. For that purpose, of course, we had a look at the EO browser and Copernicus data space ecosystem first. However, looking closely, we noticed some issues. So in both EO and Copernicus browser, there's a clear cut in the shadows, which to our understanding definitely should not be present. But what's going on there? Where do the shadowing issues come from? Let's dig into that. The Sentinel-2 tiling scheme used for storing the data is highly based on the IGARSS. So the military grid reference system, which basically is an alphanumeric version of UTM. The 60 UTM zones are divided into roughly 110 km times 110 km tiles. However, for our considerations, we identified the overlap of roughly 10 km to be the gist of the matter. It's needed for atmospheric correction, but leads to a storage overhead of roughly 30% as discussed in the study of Bauer, Marschallinger and Falkner. But the question now is, what are its implications for the merging of the tile? So how to deal with the overlap regarding that? Let's have a look at the EO browser and Copernicus browsers again. Suppose we have some AOI and the underlying Sentinel-2 tiles. Now, depending on the position on Earth, we may have a sun azimuthal angle from northerly or southerly directions for the southern and northern hemisphere respectively. However, as a non-seasonal static merging strategy, EO and Copernicus browser prioritize first the most southerly, then the most westerly tile, both for the northern and southern hemisphere. And as a side remark, for the scene classification layer, they apply a negative buffer of a few hundred meters. Anyway, applying their merging strategy, we have a following priority queue. It's clear that we start with the first tile to the lower left, so the most southwest tile. Then the second tile has to be the one to the right, as it's more southerly than the one above. And as we continue and go on like that, a certain pattern of seams in between the tiles emerges. And you might notice that the sun rays are intersecting the tile seams, and that basically is the kernel of the brood. So suppose we are in rugged terrain. The ray not known to be obscured by the mountain on the other side of a tile seam won't be considered for atmospheric correction. In that scenario, the cow here would be considered illuminated, though it's actually not. So if you have a look at the image to the right, it shows the effect using an example of a southern Patagonian ice field. And again, we have a clear cut in the terrain shadow corrections, and there definitely should not be. What about clouds? Actually, the same happens. A cloud on the other side of a tile seam will not be considered by the atmospheric correction scheme. And that, again, looking to the example to the right, emerges in a clear cut in the shadow masks. But what can we do about it? So we thought of that, and to answer this, we considered the orbits of Sentinel-2 in the regard of sun azimuth angles. For that purpose, we used all acquisition plans of 2021 and calculated the azimuth angles for the center lines of the orbits. In the figure, you can see varying them over the day of the year. Right now, we see the orbits in autumn season going from northern summer to northern winter. And while doing so, in some areas, they cross the horizontal gray dashed lines. Crossing such a line means that the orbits show changing azimuths in that latitude region. And changing azimuths in the sense that the sun could come from northern or southern directions depending on the season. And then we aggregated that over time and we extracted the latitudes of northern, changing and southern azimuths. Hence, the following seasonal merging strategy has been derived. The northern azimuths ask for a merging strategy of northerly first, then easterly. The changing azimuths cannot clearly prioritize any directions. Hence, we use the center lines of intersections. For the southerly azimuths, we have to use a southerly first, then easterly strategy. So now one could say, oh, yay, that's the end. But no, it's actually not. Because, for example, the question emerges, what happens at the boundaries of emerging strategy zones? And maybe the fact, so at this point, maybe the fact can be of help that the strategy for LCA is potentially static. Let's recap what we've seen so far. Our seasonal strategy asks for an elaborate pre-processing of the orbit. So remember the whole center line thing. Accordingly, it asks for a dynamic provenance approach depending on the latitudinal position, but it solves almost all shadow issues. A static merging strategy, however, allows parallel scheduling of the areas to query. It fosters the provenance, and actually it's easy to get a unique identifier per pixel, and it solves the majority of shadow issues. The majority of shadow issues. What about the shadows at the seams? So considering our centerline concept for the LCA from the slide before, if you remember, the question arises if 5 km are large enough. Well, we asked ourselves, what's the maximum allowed height difference in 5 km distance to the tile boundaries, depending on the sun elevation angles calculated for the center lines of the Sentinel-2 orbits. Considering both the highest mountain and the largest mountain face on Earth, so the Mount Everest and the Rakaposhi, we see that already huge height differences, such as for the Mount Everest, would be covered. But things like the Rakaposhi cannot, even if a maximum overlap of 10 kilometers, so that's basically the overlap distance here in the green line, even if that is applied, it would not be covered. Fortunately, the Rakaposhi does not lie in an overlap area of a grid. So actually we consider 5 km being enough for most cases. And at this point, let's be lazy. Let's use the static LCA strategy. But for doing so, do we want to define the polygons by hand? No, of course not. I mean, we already said it, we're lazy. So let's ask Voronoi for help. As you can see, the tiny little Voronoi centroids are already working for us. Based on the geodesic distance measure, they are finding the areas where respective distance to their point of reference is minimal. And that's basically the magic behind. The polygons are completely defined by their points of reference. So, and that's a consistent way to define a grid. But we want to get a grid, and we have to ask ourselves what makes us consider the result of such a definition consistent. So we consider a set of points, so a set of points of reference, we consider them as Voronoi consistent if the resulting grid overlay covers the whole area of the original tiling scheme, if its cardinality is as small as possible, so only a single pore per tile, and the pores are as close as possible to the centers of their tiles. However, the Sentinel-2 grid is not natively Voronoi consistent, which means that only by taking the centroids of the original tiling scheme, we do not result in a Voronoi consistent grid overlay. But why? Some unnecessary tiles and UTM inconsistencies close to Norway cause issues which make the Voronoi grid of the centroids not form that Voronoi consistent grid. Namely, Norway expanded the UTM zone 32 to the west, and that caused some non-alignments as you can see here. So here it shifted to the west, and you can see that even in the north it's still affected by that shift. And that causes the emerging grid not to be Voronoi consistent. To address this, we defined local optimization problems, and we allowed them to vary positions of the centroids or even removing them entirely. And please note that we handle every edge of a polygon as a geodesic line to mimic spherical computation, especially as the areas of interest for the local optimization problems are in the far north. So here and here, which actually rather north. So projection issues are really relevant. And after that, in the end, we identified 235 as redundant and optimized 42 centroids. And finally, we achieved a Voronoi consistent grid for Sentinel-2 queries. And here it is. Nice. But maybe it does not look any different to you to the original grid. But actually it is. Let's get back to blocking. To the left, there is the southwest merging strategy, such as for the Copernicus browser, and to the right is our proposed Voronoi consistent merging. And to the right, we don't have a clear cut anymore. Clear cut, no clear cut. The same for the southern Patagonian ice field, no clear cuts anymore. And the same holds true for the cloud shadows in the South Patagonian Pampa, no clear cuts anymore. That is, we actually solved the issues. Yay! So what did we do? We discussed static and seasonal merging strategies and its implications for rugged terrain and cloud shadows. As a solution to the emerging issues, we proposed a Voronoi consistent grid overlay. And at this point, let me emphasize this. Besides solving the atmospheric correction issues, it defines the queryable area per tile, so not by interactions in between tiles or on runtime. That fosters provenance and makes it easy to acquire a unique ID per pixel of a compound. And last but not least, there's no compromise on efficiency necessary. And that's potentially the most important point to get from this presentation. We did not propose a new way of processing the data. We simply changed the way of loading it from storage. And by that, we achieved the consistent results. That is, a correct merging strategy is crucial for both efficiency and consistency of satellite data, especially in the southern hemisphere, since there's beautiful satellite imagery as well. Thank you very much for your attention. We are very open for discussion, and if you want to download the grid overlay, just scan the QR code and reach out if you like. Bye. Thanks.